into it. As you all know, I've been interested in alleged UAP materials. So how would you analyze materials from a UAP? Well, like I said before, it's you take it apart piece by piece, you try to understand the components, and you try to ask the question, why is this component here next to that component, and what might they be doing with each other? So, but it's not just about that. It was about that there's data out there, that something unusual is observed, and the speakers this morning went over this, and the evidence is collected at a crime scene, and I got interested in it because of this. And so, but as it turned out, some of this evidence appeared to come from UAPs. Is it the steering wheel? Is it their version of a television screen? What is it? What did they leave behind, and why did they leave it behind? Is the question. So how do we analyze it? So, I mean, I won't go into all of this whole slide, but I mean, it's really about using the tools we already have, and I happen to have laboratory tools that allow me to look at metals. I'm not a metallurgist, but I play one on TV. But it's, I had the tools, and I had the interest, and I had a good friend by the name of Jacques Vallée, who brought me some of these materials, because he said, hey, let's look at this. And I should say right up front, Jacques and Hal Puthoff, Eric Davis, Colm Kelleher, all those people, frankly, rescued me from the rabbit hole of ufology, because I was wandering, and they said, here's a guy who we might be able to work with him. So it's all about, and also functional analysis. Just knowing what a thing, how it's made, is not the same thing as knowing how it functions. So, but it needs that interdisciplinary team. That what happened in the Department of Genetics. Okay, so how to do science right. So where do we start? That's who I see when I look in the mirror. So where do we start? Let's get this show on the road. That's ChatGPT, I love it. So the first case, and this is the case that we published in basically last year, and it was with Larry Lemke, a postdoc of mine, and Jacques, sorry. And so, again, it's about the evidence. You can't just take anybody's claim that something is the truth. So this is one of the best and most widely observed at the time of cases. Multiple observers, et cetera. I won't go through them all, it's not necessary. But a hovering object, and then something seems to slough off and drop to the ground. And some people were like, they were literally only within about 500 or so feet from it. So the police, luckily, were called. And here's one of the observers down here in red, another observer, and this is where they ran to, and what did they find? This is one of the actual original photographs. We have them. It's a big pool of metal that was in the process of cooling. Okay, so how did that get there? So, they went through all of the possible reasons it could get there, from hoaxes through thermite, through a meteoric crash. I mean, who would think this is a meteor? It would have left a hole. Space debris re-entry, all of these things were dismissed. So, but of course, it's just something sitting in the literature. And this is where we published that paper. And just, so there's always this question I get about reputational damage. So Sezhoon Jiang is on this paper. He's now assistant professor at Harvard and over in the medical school. Didn't hurt him. They fought for him. There's Sezhoon right there. So the first technology that we brought to this is one of the ones that was developed in my lab, actually by Mike Angelo, who's here. Michelangelo. Reincarnation. But he is. I mean, when he showed up in my lab, I thought he was crazy, because he was all excited about something that he thought we could do. And I thought, you know what? It sounds possible. So let's do it. So we took these materials. We had a big chunk of this material. We took 5 different pieces of it, very small pieces, because these things require tiny amounts of material to study. because you don't want to look at just one thing if you can. As long as, if it's relatively inexpensive, you want to look at multiple places. You want to, as we say when we're looking at the tumor immune interface, we want to sample the ecosystem. So took multiple things just to make sure. So, you know, the first thing, as you all know, we went and looked at isotope ratios. We didn't find anything. They looked absolutely normal. But I noticed something in these signatures, and those are the metals that came out, is that the ratios of the elements were different from one to the other, right? So that means it was not homogeneous. Somebody didn't put it in a blender and make a uniform distribution. I mean, if you're making a material for something and it is different in different places, then you're going to have structural issues where one part might be less or more bendy than another, or more likely to crack, et cetera. So that was interesting. That means when this stuff, when it was dumped there, however it was, but we'll take the word of the, because it's fun, right? I mean, speculation ends up being a headline, Stanford professor says, Harvard professor says. You know, no, it's speculation. It's just a game to play in your mind. So you have these different ratios, which means that before it was dumped out, it was incompletely mixed. So what does that mean? How and why would you do that? I mean, were you offloading something that was problematic? You know, we all heard the stories about how these things might wobble, and then something happens, another one shows up, and they fix it, and then they go off merrily ever after. So, and these were just the ratios. And there they are. So they're not slightly different, they're completely different, right? So everywhere you look, I've explained it before, like you have chocolate and vanilla ice cream along with strawberry, you let it melt, you give it a couple of twirls, and wherever you look, there's going to be a different ratio. So what can we conclude from this? It's clearly the result of an industrial process. It's not the machine. Maybe it's exhaust. Maybe, who knows? We don't know. It had incomplete mixing of components. That's a conclusion, right? I always talk about data and conclusions, that, you know, it's about the data, not the conclusion. Get another scientist to agree with the data, that the data is real, and now you get to ask them why. The onus is not entirely on you, right? There was no signs of any technology and no exotic isotope ratios. Okay, so, you know, can we look deeper? I mean, that's a pretty high, that's from a, you know, a structural analysis point of view, if I'm talking about atomic, you know, machines, this is like the 30,000 foot, but it's what was available at the time, and it wasn't really something that I had thought about much. But then, you know, can we do this? Can we see smaller? And why would we want to do that? Well, like with the immune system in cancer cells, the proximity of where one is relative to another actually predicts the outcome of the cancer and whether the therapy will work or not. So we went to this instrument. This is atomic probe tomography. And atomic probe tomography is actually a very well-known and used technology, but it's expensive, and there's only a few of them around. But what it does is it literally takes the sample apart atom by atom, about 1,000 atoms a second, and it figures out where the three-dimensional placement in that. So here's the idea. You create an electric field differential. You set it up so that you are evaporating the sample, and where it lands on the detector can be triangulated back to where it originated on the sample. And what do you get from that? You get a map of where things are. So this is the world's, at least public, first UAP alleged material studied at the atomic level and collected at the atomic level. So this is the Council Bluffs. It's a tiny, tiny thing. I mean, it's like literally 2 or 3 microns cubed, but there's millions of atoms in there. So, I mean, I knew that I wasn't going to find any structures, but this was an easy thing to start with. And then you look at the complexity of what's in there. So the first thing that, for instance, they were trying to explain this thing away as it's just industrial steel. Well, it's not industrial steel. Now we literally have things that industrial steels don't normally contain. But now we can go in and look closer. So here, for instance, this is 3D. Now we're inside the structure. I've taken away the iron, which is so prevalent as to be, would obscure everything. Now we can see the position of where everything is, right? Again, this is just a trial, but now we get to see potential structure. So I would say that if we're going to study any of these other materials that seem to have novel properties, this would be the way to do it. I had hoped to do the bismuth magnesium case before we tried it, but it fell apart in the instrument under the stress of the local forces. It was just too crumbly, unfortunately. There's a way to fix that, but we couldn't do it in time for this. Because that would have been cool. I think that would have got a bunch of us jumping up and down, but I'm going to do it anyway. It's coming. So you can look at all the individual atoms. You can't really see it so much. So those are the things that I showed you on the other page. Those are the individual atoms. Individual elements. There's some hints of potential differences here, but it's such early stages that I don't dare repeat. I don't dare say it until I repeat it. There's a lot more. I'm not an expert yet in APT, but I will be, in this. And by the way, this was, so the individual who's been helping me is Alex Bolton. You've seen him around. So he actually helped create all this analysis, and because we just got the data Friday. And while I was busy frantically dealing with Stanford administrative messes, he basically saved my bacon on that. But there's data, right? Now this is data. Material shows no sign of technology. The material is clearly the result of an industrial process, and it was incompletely mixed. Okay, so why? Again, that's the question you ask all the time when you see data. It's like, why? Why would you do it? What could have generated it? And why would you dump it in the middle of a field in a small farming town in Iowa? I don't know. I don't know the answers. Okay, so that's one case. There's another famous case, Ubatuba, 1950s. There's a primary witness, but we don't have it. Nobody ever had access to the primary witness, but a Brazilian journalist who received the evidence, and again, through the offices of Jacques, I was able to get access to some of this stuff. This is actually what I don't quite understand, is because, as you'll see from the result, it was claimed to be pure magnesium. What I was given was not magnesium. So, but we have two things called moisture A and moisture B. And that's Spanish for sample, I think somebody said, told me. And then this is the instrument that we used, highly accurate mass spectrometer. And just, this is the beginning of sort of how science is done. You don't want to measure different things on different days, because you want the experiment to be done under the most similar conditions that you can. So those samples, two examples of each of those samples, along with a zoo of other things that Jacques happened to have, were put on this, and then we did the analysis. And I remember sitting there when they printed out the data, and I was like, I don't understand this. I mean, I hoped something like this would happen, but I never understood it. I still don't. So one of the samples, claimed samples, has pretty much exactly the natural thing. We had two shards of each. The other one was way off. Way off. I mean, just no doubt. Okay, so why? 1950s, isotopes. If you mentioned isotopes to a 1950s crowd, they'd duck and cover, right? Because isotopes, and still, humans use, like one of the most important things we do is we make nuclear bombs out of them. Of course, they're used for medical purposes and tracing. But we don't have any chemical or material reasons to use them. So, okay, so what's going on? So one had not, why change the isotope ratios? Back then, it was extraordinarily expensive to do these kinds of separations. It's still expensive. I mean, my lab orders extremely small amounts of different isotopes from the lanthanide series, because we use them as tags in our biology experiments, because each of them is unique. So for the uninitiated, what are isotopes? Again, this is, thank you, ChatGPT, and it made some things up, of course. But, the idea here is, humans work with elements. But somebody is playing with isotopes. So why would you play with isotopes? Because they're supposed to be the same. That's what I was taught in chemistry. Well, it turns out that's wrong. Now, people are starting to look at isotopes because you have an extra neutron in the element, and that changes the electronic configuration of the orbitals just slightly. And so in the right circumstances, having that difference would be sufficient to make a better catalyst. And so people, pharmaceutical companies and others, are starting to use this, starting to understand that, hey, there's something interesting here. Silicon, some of the isotopes of silicon make better qubit holders that last longer than others, than the other three. Okay, so there it is. I mean, it's there. Plants use it. Actually, it's really fascinating. So there's something yet to be understood. Okay, so this was the first time that I had gone beyond just magnesium, looking at the Ubatuba material. And even though we looked at the magnesium, because that instrument that I just showed you can see down to the parts per million, we were looking at that level. When I looked at this, it was almost entirely pure silicon. Okay, well, what's the natural state of silicon? Sand. Silicon oxide, quartz, things like that. It doesn't come prepackaged as 99.999395. You just don't get it. So why is somebody tossing that level of purity around? Because again, that would be expensive to make. So why would you do it? So again, we go in and we're collecting this data. And by the way, I'm showing all of this because all of this will be going eventually on the web, and I want to do this with every material that I can get my hands on legally. Like, I'll be like Lou and Chris sneaking something out the back. They weren't. I'm sorry. Chris is going to kill me. Good. And so again, look at the numbers there of the percent. There's lots of other things in there, but the vast majority is silicon. The reason why it shows as lower is because I broke it down into the silicon isotopes, and they're natural levels. So here again is the 3D, where we can go inside, and so one of the next things to do is to say, well, is there any sort of strange placement of the atom? So those are the three nucleotides. And is there a likelihood for one thing to be near another? And that's what we do, again, in immunology. We look for certain cell types that are more or less likely to associate with each other. And that tells you that, if that happened above statistical chance, then there's probably a reason for it. Things don't happen, usually in biology, by coincidence. The two samples are pretty much within statistical certainty to be similar to each other. So that's interesting. So even though they came from separate chains of custody, there's enough data here, at least, to say that whoever prepared this stuff either had identical preparation techniques, or it came and it was broken and given into two chains of custody. Again, it's data. No sign of technology, but certainly signs of an industrial process. And that's important. So, I'm saying this thing about the silicon. If anybody can tell me why pure silicon should be thrown around a beach in, Brazil, I want to hear it. you know? So the material is clearly a result of an industrial process. It wasn't found randomly. Nobody found it on the side of a road. It was associated with an event. And that's important here. And because that coincidence, it doesn't prove that it's anything, but it makes it, to me, more interesting. Unusual levels of pure silicon with contaminants. So again, what would you do? So the event was somebody saw something supposedly with lights, and then it dropped something which exploded. Okay. Why? Right? Why? What's going on? I don't understand. Because on the one hand, we have these metals that drop. I have another sample of something from Australia. There's a couple of other events that actually are dropping molten objects. So there's a reason to offload something. Again, I'm speculating. There's a reason to offload something, but every time they do it, it ends up being slightly different. So does that tell you that there's many ways to achieve a similar goal? Right? So that's kind of sort of back engineering the thought process of why would you do something like this? So here's another case, very famous case, Socorro. Again, this is something from Jacques. On an Indian reservation, the police officer was Indian. He's driving along. He hears a noise. He sees something, a shiny object in a field. He observes little people outside of the object. The object takes off kind of with a burst of flame. And of course, when people tried to debunk it, they said he saw the star something or other. He's a trained observer. He's a policeman, right? So he didn't want to talk about it, so he wasn't seeking publicity. He just did it. So Jacques had a piece. He gave it to me. Again, we take an electron microscopy. Everything looks like it's, from another planet under an electron microscope. Very simple. Aluminum, zinc, mostly, and some contaminants. But the aluminum and the zinc are in different places. So this is at a distance. So there it is. So there's the aluminum on the top, there's the zinc on the bottom, or vice versa. No, zinc's the green, yes. But it's differently distributed. It's the contaminants that are interesting. That's what I'm interested in, because they're kind of a signature. Are they uniformly distributed throughout the thing? Meaning, or are they somehow next to each other? So we looked at that. So now, if I look in the aluminum on the top, again, it's incredibly pure. It has like a single oxygen molecule amidst a million. I don't know who does that, and why would you do it? It's attached to a zinc thing underneath, which has some aluminum in it, but look at how it's non-uniformly distributed. Right? There's like a cluster of it over here. Is that because they have a junky recipe? They didn't mix it right? It just is. But why? Don't know. Again, this case, this is clear sign of engineering. The interface between those things is like exact, down to the atom. It's clearly the result of an industrial process.